So let us start. So if you remember, in the last class we were proving the Rees theorem, and we were proving actually the converse part of Rees theorem. Okay, so we were proving the converse part of Rees theorem. So converse part of Rees theorem. Converse part means we have to show that actually we were proving that we have to prove that a completely zero simple semigroup S a completely zero simple semigroup S is isomorphic to a Rees matrix semigroup. Is isomorphic to a Rees matrix semigroup. Rees matrix and in fact we have started the proof of this theorem. Suppose S is a so if S is a completely zero simple semigroup, if S is a completely zero simple semigroup, then semigroup with primitive idempotent with primitive idempotent E. So we have proven some. So we need to prove some lemmas, and lemma 1 we have proven. Lemma 1 was the R class of this idempotent E, that is RE equals ES minus 0. So this was lemma 1 that we have proven. Okay. Now a few more lemmas before we finally get this theorem. So now we have lemma 2. Lemma 2 is actually a generalization of lemma 1. Lemma 1 says that R is equal to ES minus 0, where E is the primitive idempotent. But lemma 2 says that for every non-zero element, for every A not equal to 0 in S, or class of A equals AS minus 0. Okay. Now proof of this lemma. Now if X belongs to R class of A, then X is R related with A. And so X is going to be equal to X equals AU, A equals VX, A equals XV, sorry, A equals XV for some UV in S1. For some U and V, for some elements UV in S1. Okay, now X is X equal to AU. From this equation, X equal to AU, it implies that X belongs to AS. Okay, and X is not equal to 0 because, and X is not equal to 0 as X equal to 0 implies A equal to 0, V equal to 0, which is not possible, which is not possible. So we get that X is an element of AS minus 0. It's a non-zero element. So we get that this R class of A is contained in AS minus 0. Okay. Now see the reverse inclusion. Conversely, let choose an element, say B belongs to AS minus 0. So by zero simplicity of S, by zero simplicity of S, so B is a non-zero element of S. So there exist some elements, say Z and T in S such that A equals ZET, where E is permittive idempotent. E is chosen as earlier, where E is chosen as earlier. Okay, now B is an element of AS minus 0. So B equals AS for some S in S. B equals AS for some S in S. So B equals AS. B equals AS for some S in S. Okay. So thus B equals no, ये B के लिए हम कर रहे हैं. This is for B. Sorry. ये जो B की वैल्यू है, because B is non-zero, so this we are doing for B. B equals ZET, where E chosen as earlier. ना बी की दूसरी वैल्यू भी है आपके पास, बी आपके पास ए एस आ जाएगा। सो देन बी इक्वल्स जेड ई टी एस। नो, हाँ ठीक, नहीं नहीं, ये ए की वैल्यू है, सॉरी, ये ए के लिए है। सो दिस इज फॉर ए। सो बी इक्वल्स जेड ई टी एस and this is equal to Z EU, where U equals TS, where U equal to TS belonging to S. Okay. Now, EU, what is EU? EU equals, EU is a member of ES. EU belongs to ES. And ET also belongs to ES. And ET belongs to ES. And EU is not equal to 0. And EU is not equal to 0 because EU equal to 0 implies ETS equal to 0, and which implies B equal to 0, which implies B equal to 0. But B here is chosen as a non-zero element. Okay, so what we get from here is that, now similarly ET is also not equal to 0. Similarly, ET is also not equal to 0. Thus we have that, thus we have that B equal to EU, B equal to B, no, what we get from here is that हमारे पास अब क्या आ गया, EU भी नॉन जीरो है और ET भी नॉन जीरो है. So we have that this EU belongs to ES minus 0. Okay, and ES minus 0 is RE by lemma 1, by lemma 1. Okay, and moreover you have ET also belongs to ES minus 0, which is also equal to RE again by lemma 1. Okay, so this means what? This means this EU is R related to, so this means this EU is R related to E, and E is R related to ET, R related to ET. Okay, now combining these two, because now R composition R is R, so EU is R composition R related to ET. It means EU is R related to ET. And R is a left congruence. We know this. So by left congruence property of R, by left congruence property of this equivalent Green's equivalents are, you get that ZEU are related to ZET. But ZEU is B. This is B and this is A. So this implies B's are related to A. Okay. But B you have chosen in AS minus 0. B you have chosen in AS minus 0. So this means B belongs to R class of A. So this means this AS minus 0 is a subset of R class of A as required. Now this proves the lemma 2. So in lemma 2 we have proven that for every non-zero element A in S, R class of A is equal to AS minus 0. Now similarly you can prove the dual part of this lemma, and that is lemma 3. So a dual version of lemma 2, a dual version of lemma 2 can be shown in a similar manner. Can be shown in a similar manner. And it is in fact the following lemma, which we call as lemma 3. It is for our classes actually. It says that for every A belonging to, for every A non-zero in S, for every A non-zero in S, L class of A is same as SA minus 0. SA minus 0. So this is lemma 3. Okay. Now we have another lemma. So we have another lemma. What is that? In fact, that is lemma 4. So lemma 4. Lemma 4 says that ये जो हमने completely zero simple semigroup S choose किया था ये regular भी होता है. Lemma says that S is regular first thing, and has exactly 2 D classes. And has exactly 2 D classes. What one is D, one is 0, one is 0, and other is S minus 0. S minus 0. Also, the other part of the lemma, if AB they belong to a D class D, then either their product AB is 0 or this product AB belongs to this class or a intersection LB. And the later happens. So the later happens if and only if LA intersection RB contains an idempotent. Contains an idempotent. तो ये जो लेमा 4 है इसमें हमें बहुत सारी चीजें देखनी है। पहला हमारा क्लेम है कि ये जो एस है ये रेगुलर है। इसमें हमें क्या क्या देखना है? एक हमें देखना है कि एस रेगुलर है और इसमें सिर्फ दो ही डी क्लासेस हैं, एक 0 है और दूसरी एस माइनस 0। ठीक है, ये हो गया इसका फर्स्ट पार्ट। सेकंड पार्ट कहता है कि अगर कोई भी एलिमेंट आप चूज करोगे इस डी क्लास में, या तो उनका प्रोडक्ट 0 होगा या उनका प्रोडक्ट इस एच क्लास आर ए इंटरसेक्शन एल बी में लाई करेगा। और आर इंटरसेक्शन एल बी में लाई करेगा इफ एंड ओनली इफ ये जो एल ए इंटरसेक्शन आर बी है ये आइडमपोटेंट कंटेन करेगा। सो दिस इज व्हाट लेमा 4 says. Now let us write the proof of lemma 4. Now let AB belongs to S minus 0. Let AB belong to S minus 0. Then we claim that this ASB is not equal to 0. Since ASB equal to 0 would imply that since ASB equal to 0 implies that ASB equal to 0 implies that S square, which is SS. Now by 0 simplicity, S is equal to SAS. Again by 0 simplicity, S equal to SBS. Okay, and then you can write it as SASBS. If this is 0, then this is going to be 0. So this means S square equal to 0, which is not possible as S is 0 simple, which is not possible. Okay, so if you choose AB belong to S minus 0, then ASB is non-zero. Okay, so ASB is non-zero. So this means there must exist some non-zero element here. So let U belong to S. Let U belong to S be such that the product AUB, which is equal to C say, is non-zero. ये non-zero है तो इसमें कोई non-zero element होगा, and that we are saying that ये वो AUB है. Then C is AUB. Now AUB is an element of what? it belongs to as minus 0, and it also belongs to sb minus 0. It also belongs to sb minus 0, है ना, क्योंकि ये ए एस टाइप का एलिमेंट होगा, फिर इधर से अगर आप देखेंगे ये एस बी टाइप का एलिमेंट होगा. सो इट बिलोंग्स टू ए एस माइनस 0, एस बी माइनस 0. सो this C actually belongs to AS minus 0 intersection SB minus 0. But by lemmas, we have just proven AS minus 0 is actually RA, and this is actually this is LB. Okay, by lemma 2 and 3, by lemmas 2 and 3. Okay, so this means what? C belongs to RA intersection LB. So this means C is R related to A and C is L related to B, and C is L related to B. Or in other words, you can say that A is R composition L related to B. So this means A is D related to B. Okay. So this means what? Any two non-zero elements of S, they are D related, because you have chosen A, B, be any two non-zero elements of S, and you have shown that they are D related. So this means what? This means that the S minus 0 belongs to a single D. S minus 0 is D. S minus 0 is D. Okay. तो हमने ये वाला पार्ट कर दिया, इसका पहला पार्ट, इस लेमा का. नहीं, इस पहले पार्ट का कुछ हिस्सा कर दिया. हमने ये कर दिया कि S has exactly 2D classes. एक तो 0 है, दूसरी S minus 0. ये वाला हमने कर दिया. So thus S है. So S has exactly 2D classes. Since अभी हमने शो किया D इक्वल टू S माइनस 0 है. सो अगर D आपका S माइनस 0 है और S जो है S में परमिटिव आइडम्पोटेंस है, इसका मतलब D में भी एक परमिटिव आइडम्पोटेंट है. So thus this D equal to S minus 0 contains an idempotent, a primitive idempotent. तो idempotent हमेशा रेगुलर होता है ना, E equals E. तो इसका मतलब D क्लास, ये जो D है इसमें एक रेगुलर एलिमेंट है, और हमारे पास एक रिजल्ट है. So this means D contains a regular element. D contains a regular element. A regular element. तो हमारे पास एक रिजल्ट है. अगर आपने देखा होगा, we have this proposition 2.3.1 in the book of Harvey. आपने ये पहले कोर्स में पढ़ी होगी. ये कहती है कि अगर कोई भी डी क्लास जो है या तो उसमें कोई भी रेगुलर एलिमेंट नहीं होगा या सारे एलिमेंट रेगुलर होंगे। मतलब अगर उसमें अगर एक एक एलिमेंट रेगुलर है तो सारे एलिमेंट उसमें रेगुलर। ये प्रोपोजिशन की स्टेटमेंट ये है, इफ A is a regular element of a semigroup S, if A is a regular element of S, then every element of DA is regular. उसकी D क्लास में हर कोई एलिमेंट रेगुलर होगा। Then every element of DA is regular। ठीक है, तो हमें यहाँ से क्या मिला कि ये आपका जो D है ये रेगुलर मीन्स S माइनस जीरो हमारे पास रेगुलर आ गया। सो दिस मीन्स D equal to S minus 0 is regular। लेकिन जीरो भी तो हमेशा रेगुलर होता है। since 0 is always regular, since 0 is always regular, what we get, it implies that S is regular। S is तो हमने इसका ये पार्ट भी लेमा का कर दिया। ठीक है, ये पार्ट S is regular हमने ये भी कर दिया, S is regular and has exactly two D classes, ये तो पहले ही कर दिया था। अब हम ये वाला करेंगे, अगर कोई भी एलिमेंट होंगे जो जिनकी डी क्लासेस सेम होंगी, मींस अगर वो डी रिलेटेड होंगे तो या तो उनका प्रोडक्ट जीरो होगा या वो प्रोडक्ट आर ए इंटरसेक्शन एल बी में लाइक करेगा। लेट अस सी इट। सो हम मानते हैं ए बी इज नॉट, सपोज द प्रोडक्ट इज नॉट जीरो। नाउ सपोज द प्रोडक्ट ए बी इज नॉट इक्वल टू जीरो, देन ये तो पहले से ही आ गया, ए बी कहाँ बिलोंग करता है, ए बी बिलोंग्स टू ए एस माइनस जीरो intersection SB minus 0, SB minus 0, and again which is equal to RA intersection LB। तो अगर प्रोडक्ट नॉन जीरो है so it belongs to RA intersection LB। और हमारे पास एक रिजल्ट है, this is a proposition 2.3.7 2 point आपने पढ़ा होगा ये। Let A B be elements in a D class D, let A B be elements in a D class, in a D class D, then this product AB belong to RA intersection LB if and only if LA intersection RB contains an idempotent। If and only if LA intersection RB contains an idempotent। ओके, तो हमारे पास आ गया ए बी नॉट इक्वल टू जीरो implies AB belongs to RA intersection LB, and this happens if and only if LA intersection RB Okay. So the result now follows from this proposition. The result now follows by above proposition. The result now follows by above proposition. तो हमारे पास हमने ये लेमा प्रूव कर दिया. लेमा सेज दैट जो हमने कंप्लीटली जीरो सिंपल सेमी ग्रुप लिया था एस, वो रेगुलर है. उसमें सिर्फ दो डी क्लासेस हैं, एक जीरो और एक एस माइनस जीरो. तो अगर कोई भी एलिमेंट आप दो चूज करोगे किसी डी क्लास में, या तो उनका प्रोडक्ट जीरो होगा या फिर प्रोडक्ट बिलोंग करेगा इस आर ए इंटरसेक्शन एल बी, जो कि एक एच क्लास है. And the latter happens if and only if this condition is satisfied. Okay. Now this proves lemma 4. Now after proving this lemma 4, we are heading to. So let us take an H class. So let H be an H class contained in the D class. So let H be an H class. H class, you know, H relation, which is the intersection of L and R. Let H be an H class contained in the D class D, contained in the D class D, which is actually S minus 0, and let A be belong to H. Then by above lemma 3, sorry, by lemma 4, then by above lemma, the product AB belong to, so the product AB belong to RA intersection LB, which is H, or the product AB is 0. Now in the former case, in this case, H is a group by Green's theorem. In the former case, H is a group. And this follows by Green's theorem. If you know Green's theorem, it says that you must have studied it. Green's theorem says that if you have an H class, H, then either H square intersection H is empty or H square is H. And H square is H means H is a group. So let me write the theorem statement. Green's theorem. It is the theorem 2.2.5 in the book of Howey, 2.2.5. Okay, so it says that if H is an H class, if H is an H class in a semigroup S, in S, either then and this H square intersection H is phi, or H square is equal to H, and H is a subgroup of S, and H is a subgroup of S. तो कोई भी H क्लास अगर आप लोगे, या तो H स्क्वायर इंटरसेक्शन H एम्प्टी होगा, अगर नहीं होगा तो फिर H स्क्वायर H होगा और H ग्रुप होगा. तो हमारे केस में H स्क्वायर इंटरसेक्शन H जो है वो नॉन एम्प्टी है. इन अवर केस H स्क्वायर इंटरसेक्शन H इज नॉन एम्प्टी, बिकॉज हमने हमारे पास है ना ए बी जो है वो H में भी है, और एंड ए बी जो है वो H स्क्वायर का भी एलिमेंट है. So this is non-empty. Okay, in our case this is non-empty as we have this. So therefore by Rees theorem, H square is H and H is a group subgroup of S. So therefore H, you have in the former case H is a group. This is true. And in the later case H square is equal to 0. And in the later case H square is equal to 0. Why? Because if you choose any two elements for if C and D are arbitrary members of H, C comma D are arbitrary members of H, so this means what? C and D, they are H related. Okay, so therefore they are also R related as well as L related. So by definition of L and R, there exists some element, there exists some X and Y in S such that the C equals XA by definition of L, and D equals BY. And then if you take the product CD, any means C and D are members of H, so the product CD, it is an arbitrary member of H square, and this is non-zero because CD equals XA BY, CD equal to 0, sorry, and this is equal to X A B Y, and AB is 0, so this is 0. So if you, what does it mean? It means that if you take any H class in a D class, which is a regular D class in fact, then either if you take any H class within this regular D class S minus 0, okay, and you choose any A B in H, then ऊपर वाले लेमा से ये आपके पास कंडीशन होगी, या तो ए बी आर इंटरसेक्शन एल बी में होगा जो कि एच होगी, या ये प्रोडक्ट 0 होगा. अगर पहली कंडीशन होगी तो एच ग्रुप होगा, अगर दूसरी कंडीशन होगी तो एच 0 होगा, एच स्क्वायर 0 होगा. एच स्क्वायर 0 होगा मींस एच भी 0 होगा. ओके, सो देयरफॉर व्हाट वी कैन से दैट कोई भी एच क्लास अगर आप चूज करोगे किसी भी डी क्लास के अंदर, या तो वो 0h क्लास होगी या ग्रुप H क्लास होगी. So we may refer to the H classes within D as either group H classes or 0H classes. Either group H classes or 0H classes. Sorry, 0H classes. Okay. So I think I will stop this lecture here, and the remaining part of this theorem we will do in the next class. So if you have questions, you can ask. Any questions? Yes. CR. Roll number 1. Any question?
No, sir.
ठीक है, आज हम इतने रखेंगे. So let us see tomorrow.
Okay, sir.
Okay, sir.